This presentation is delivered by the Stanford Center for Professional Development.
Oh, okay. Then I guess we'll just start. We'll start in. It's going to be interesting. Well, okay. I guess I should have a laser pointer. I'll bring one next time or something like that, so I can point to various things. Okay. So where we're going to start. We're going to start today from the idea. So last lecture we looked at the idea of a subgradient, which is essentially it's a generalization of the idea of a gradient, but for a non-differentiable problem. Actually, there is another generalization of a derivative to a non-differentiable problem. We're going to see that other definition soon, and in fact, they're going to be duals in a certain sense. So we're going to see how that works. So subgradient is one. It turns out it's actually the useful one. The useful one is the subgradient one. Useful in terms of many things, like for example, if you want to come up with simple algorithms to optimize things, subgradients are very, very useful. Okay. So last time we got as far as this, we said that we observed that if you have a subgradient of a convex function at a point, that's g is a subgradient of f at x. Now, of course, there can be many subgradients, but just if you have any subgradient, what it tells you is this. It gives you essentially, I mean, here's a point. I can actually reach this without a laser pointer. So here's a point where there is only one subgradient because it's differentiable here, and it's the gradient. It points this way. And what this tells you is that this entire half space here, this whole half space here, has a function value higher than the value at this point x1. And that means, for example, if you wanted to minimize that function f, there would be absolutely no reason to consider this half space. So another way to say it is a subgradient rules out an entire half space from consideration. So that's what a subgradient is. And by the way, that's true if the function is convex or not. It just happens only to be useful in the case when the function is convex, because it's actually true. I mean, this is true even if the function is not convex. The problem is you'll never know. You'll never find. There's no way to find a subgradient and so on and so forth. There's no way even to know that something is a subgradient unless the function is convex. Okay. So let's look at a useful generalization of this. Occurs when you have a function that is quasi-convex. So remember what quasi-convex means. It means that you have quasi-convex means that the sublevel sets are convex. And you would typically, if you had an objective like this, you would solve it by some kind of bisection, for example. You'd ask for, if you can attain a level, that's a convex feasibility problem, and then you might do bisection, for example. Okay, so a quasi-gradient is a vector that satisfies the following. It says that if g transpose y minus x is bigger than or equal to 0, then f of y is bigger than f of x. So that's a quasi-gradient. I should warn you that if you do look in the literature, you will find tons of variations on these. You'll have like a strong quasi-gradient, a pseudo-gradient of this and of that and that. So just watch out if you look in the literature or anything like that. And so the basic idea is this. It says that if you have a quasi-gradient, something like here, it basically says that everything on what it rules out that half space. It says that everything in that half space has a higher than or equal function value from the other one. So that's quasi-gradient. So obviously, if the function is convex, a subgradient is a quasi-gradient because that's where the whole idea comes from. So let's look at some examples. The canonical example of a quasi-convex function is linear fractional. So we look at a linear fractional function on the domain. The domain is going to be the open half space where the denominator is positive. And so here, if you work out, I mean, you can just easily work out what a quasi-gradient is. It's just a quick calculation. But for example, here you calculate one this way. It's just a minus f of x0 c. I mean, this is easy. You simply write f of x is less than f of x0. or f of x is bigger than x0. And actually, that's a half space anyway. So that's a quasi-gradient. And to check, all you have to do is check is if you say you have A transpose x minus x0, if I multiply this thing out here, that's bigger than f of x0 times C transpose x minus x0. And that tells you if you simply divide here and add d to both sides here, the x and the x0, that says f of x is bigger than f of x0. Okay, so that's an example. As another example, here's a quasi-convex function, and it is the degree of a polynomial as a function of the coefficients, right? So it's just interesting because it's integer valued, and so that's what it is. And it's kind of pedantic even to call the degree quasi-convex, although it's not a bad thing to do, because the way you solve it is really silly. If you had some convex problem involving a polynomial like this, and you wanted to say, for example, minimize the degree of the polynomial that satisfies something. For example, find me the lowest order polynomial that actually satisfies some interpolation conditions or approximates something well enough. It's quite simple. For each fixed degree, it would be a convex feasibility problem to check if such an approximation exists. And then you could just do bisection. You take n, you take 0, and then you take n over 2 and round up or down. I mean, your choice. It won't make any difference. And run bisection. Okay, so here, what you need is a quasi-gradient. And here you can just work out what it is. It turns out you can just take the sign of the k plus first coefficient in the k plus first position. And you can actually just check. That's quite straightforward because you get G transpose B minus A is, well, G transpose just picks out the kth component and multiplies by AK plus 1, the sign of AK plus 1. So this will do the trick. And of course, this will imply that BK plus 1 is not 0. And that will imply, if BK plus 1 is not 0, that implies that the degree of B is at least K plus 1, which is bigger than K or whatever. So that's how that works. So these are examples. And these are not hard. I mean, these are like little exercises. Okay. Now we'll look at optimality conditions. So yeah, by the way, I want to point out we sort of, it is important to understand. So far we've done nothing but analysis. So it's math. But it's even worse. It's kind of circular math where you just introduce a bunch of definitions and then do things but never actually say anything that helps you or whatever. So that's our current state. That'll change actually later this lecture. But for now, that's the current status. Actually, the first inklings of something that you've actually done something will occur now. And they just sneak upon you very quietly. So they're really quite weird. So here it is. If you have a differentiable function, the condition is for optimality, necessary and sufficient, is that the gradient should vanish. That's it. And one way is very easy to show. If the gradient vanishes, you write down this inequality that says, let's see if this is going to work. Let's see what happens here. If a function is, who's going to be able to, we're going to have to do the sight lines very carefully here. Let's try this. So we have this. And the question would be, can anyone see that? Okay, then that's good enough. So here's your basic, your basic inequality. Obviously, if the gradient is 0, it basically says that for all y, f of y is bigger than f of x. But that's basically the definition of of x being the global minimizer of f, right? So that's simple enough. And then the other direction is also easy to show as well. In fact, the other direction you can show lots of ways. One would be to say, suppose the gradient isn't 0. If you took a small step in the direction of the negative gradient, the function would go down, okay? Which would kind of cast some serious doubt on your assertion that x was optimal. So everybody, I mean, what I just said was actually a proof, but just, in words. Okay, all right. So non-differentiable, I mean, it's really simple. It looks totally innocent, and it's this. A non-differentiable function is minimized by x star if and only if. Now here the sub-differential is it's a set. So And it's if and only if 0 is in the subgradient. So that's the condition. One way is completely trivial to prove. It's the same thing, right? Because, in fact, here's what a subgradient is. The definition of a subgradient is this. This definition of a subgradient is that for all y, this holds. But if 0 is a subgradient, it says that for all y, f of y is bigger than or equal to f of x. So one direction here is just a tautology. The other direction is just as easy as well. In fact, it goes the other way. Suppose I told you x is the minimizer of f, global minimizer. By definition, that means that for all y, f of y is bigger than f of x. That's what it means to be the global minimizer. Therefore, it's for sure true that this inequality holds when g equals 0. That means 0 is a subgradient. Okay? So now, when you first see this, you think nothing happened. That was completely trivial. That was circular. There was nothing there. So, in other words, not only is this true, but it is completely trivial. Okay. That's sort of it. But by the way, this case is an interesting one, right? And it shows you, it says that it does not say that the 0 is the only subgradient. And in fact, in this case, there are many subgradients. What you can say about the subgradients here is they straddle 0, is what happens here, obviously, right? You have negative slopes and positive slopes, but 0 is in the subgradient. One comment, weak subgradient calculus will not help you with this. Remember what weak subgradient calculus, if you want to think about it operationally, is this. You have a method that will return a subgradient at a point. So, and then the point here is I could easily return for this function at x0, I could return the subgradient minus 0.1. And it is a subgradient. There's absolutely no doubt about it. It is not 0, right? So basically what that tells you is that stopping criteria based on weak subgradient mechanisms are not going to be simple. They're not. Now, if you have strong subgradient conditions, you can do that because you have something that somehow, abstractly in some way, returns the entire subgradient. Then, of course, you have to have the containment question. Can you check if 0 is in the subgradient or something like that? Actually, we'll see there's a very good way to check that. Okay, so what's weird about it is that although it seems like we've done absolutely nothing, it turns out we actually have done something, which is kind of weird. But let's try it. So let's take piecewise linear minimization. So you want to minimize a piecewise linear function. And according to this trivial analysis, it says 0, the optimality condition is simply 0 is in the subdifferential of f at x star. But we know what that is because this is a max of a finite number of functions, and that's equal to this. It's the convex hull of the AIs where I are the active constraints. Okay, so that's what and it's a polyhedron, that thing. Now the convex hull is just, another way to say it is just that you're basically saying this. There are lambdas which are bigger than the positive lambdas that add up to 1, so it's like a probability distribution. And the expected value of the A's is 0. Okay? And I should say there's this condition. In fact, this should look very familiar. It's a complementarity condition, right? Because it basically says these lambdas here, I assigned a lambda for everybody. But up here, that's the convex hull only of A's corresponding to active ones. And therefore, I have to make this thing mean the same as that, I have to say the lambdas are 0 if you're not active. This is what it means to be not active. Okay. Yeah?
Do that again?
Yeah, we did that last time. It was, we looked at, no, it shouldn't be obvious, but it's true. It's not hard to show, but it's certainly it's not hard. It's not hard to show at all in this case. And I think we looked at that last time. So we had that was our strong subgradient formula, right? It said that if you have the max of a bunch of things, and you want to calculate the subdifferential, you would calculate this way. You'd look at you'd go to all the, in the max, you'd look at, first you'd single out everyone who's active. And you'd screen for the active guys in the max. And then for each of those, you'd ask them to produce a subdifferential at that point. Then you take the union of those and the convex hull, and that is the subdifferential of the parent of the max, the parent in the tree. There. Okay. Okay. Now this looks pretty familiar because they're exactly the KKT conditions for this LP formulation. So that's the epigraph form, and I should add, this is how you would solve this problem. I mean, anybody here, this is how you, if you had to solve piecewise linear minimization, you would do it by basically forming that. Or, for example, if you use CVX or one of these other high-level things, that would transform that for you into this top thing, this top LP, and then solve it. But whether you know it or not, you'd be solving that problem up there. And the optimality, the dual of that is this thing right here. It's maximize B transpose lambda is subject to lambda positive, and A transpose lambda is 1, and 1 transpose lambda is 1. And that means lambda is really a probability distribution. So, and this should fit well with all sorts of things. For example, suppose you minimize a piecewise linear function in R, it doesn't matter, R2. Let's minimize it in R2. And suppose when you find the optimal x, what you allege to be the optimal x, suppose only one of the functions is active there. What does it mean? First of all, could it happen? Yeah, it means it can only happen if the slope is 0, and that'd be a piecewise linear function that looks like this, right? It could only look like that. But more generically, it's going to take a couple, and that means you're going to be at a point where you're going to be at a sharp point. Okay? So that's how that works. Okay. Okay. Let's do the constrained case. I mean, it's beautiful because it's sort of the generalization. It's the prettiest generalization of the KKT conditions. So if you have optimal, I mean, I could add the equality constraints in. That's absolutely no different. It just would clutter the slide. But so here, this is the constrained case, but now F0 and Fi are non-differentiable. They are not differentiable. So you can't even talk about the KKT conditions there. So these are the generalizations of KKT conditions, and they basically are the following. Obviously, if X is primal optimal, it's got to be feasible. That's a requirement for being optimal. The lambda i's have to be bigger than or equal to 0. That's obvious. And this is the condition here. It's exactly the condition that would be gradient and gradient if these were differentiable. In the case where they're gradient and gradient, that would be equals, because the right-hand side would be a vector, not a set. Here it's a set. And of course, everything here is overloaded for sets on the right. So that's what that is. So actually the only difference is quite pretty. Is you switch out the symbol, well, you switch that to an equals, from an equals to an in, and you switch the gradient symbol to this symbol here, the subdifferential symbol. And you have to reinterpret everything properly. So these are the conditions, and they're quite pretty, and it gives you a rough idea of how these things how these work. It's actually quite easy, I think, to show. At least one direction is easy, the other direction's not hard or something like that. Okay. So now we're going to cover this second idea of a derivative. So let's go back to the beginning, and the issue is this: you want to here's what you want to do. You have a non-differentiable function, and you want to talk intelligently about a derivative of it. Well, I mean, the normal derivative doesn't exist, right? So that's, I mean, at some points it doesn't exist. Even more than that, at points that we are unusually often interested in, it doesn't exist, right? Because if you're doing L1 or anything like this, of course, if you do any kind of optimization, you're going to tend to hit these points that are at corners and things like that. I mean, that's kind of what optimization does. Okay. So one generalization is subgradient, and you've already seen kind of what it does. I mean, optimality conditions are beautiful. All sorts of other stuff comes out very nicely with subgradients. But it might not be even the first one you'd look at. The first one you might look at would be something called the directional derivative. So the directional derivative of a function is, well, it's what it sounds like. You say the directional derivative of f at x and in the direction delta x. So this is a function of delta x. Is simply the limit as h goes down to 0 from positive of x plus f of x plus h delta x minus f of x over. Now, if it's differentiable, that thing there converges exactly to grad f of x transpose delta x. In other words, if f is differentiable, then f prime exists and is a linear function of delta x. Okay? So, in fact, the linear function is grad f of x transpose delta x. Okay? Now, this function here is extremely easy to show. This thing has to be, it's homogeneous. It's always homogeneous. What it might not be is linear. And we'll see simple examples where it's not linear. But it's homogeneous. Okay, so if it's linear, it tells you this. Now, this is actually not a trivial fact, but it's, and I'm not going to go in, I mean, there's like giant books and things, many books on convex analysis that would go into the horrible details of this. But a very basic result is this, is if you have a convex function, roughly speak, I mean, let's say, and you're inside the domain, and you're in the interior of the domain, if you're away from the boundary, then you have a directional derivative in all directions, okay? So, I mean, that kind of makes sense. Let me go over here and draw some pictures. So, if you have a function like this, right, you're not differentiable there, but you have a directional derivative. And in this case, it's homogeneous, but a homogeneous function on R, a positive homogeneous function on R, you only have to say what it is from the left and from the right, right? Because if you know what it is for +1 and -1, you're okay. And in fact, in this case, f prime of x and then 1 is what we would generally call, I guess, f prime plus of x. That's the right-hand derivative, and it's this slope. And then if you do this like this, -1, that's the directional derivative in the direction -1, you get, in this case, f minus prime of x. Now, if you're differentiable, these two things are equal, and they're both coincide with the derivative. In this case, there's a gap between them. And for example, this thing, well, they're both negative, but that's less negative than that. Okay? Everybody see that? So that's, but what's interesting about this is this happens in Rn. I mean, not just R. So take some horrible function in Rn, non-differentiable, go to some point where it's got all sorts of sick stuff there. But the point is that in any direction you move in, if you move along a ray, it will be differentiable. It will have a directional derivative. Okay. Now, if that directional derivative function is linear, then it means the function is actually it means the function is differentiable. Okay. That's directional derivative. Now the question is how is it related to the subgradient? And in fact, they're related by duality, so which sort of makes sense. And I think I can, yeah. So I think we can. So here's the general formula. It says this: the directional derivative in the direction delta x is the sup of g transpose delta x, where g is in the subdifferential. And so that is the this is called the support function of the subdifferential. So to write a very compact expression for it, you'd say that the support, so you could write something like this: f prime equals, the support function subdifferential f at x. So that's just a very compact formula that tells you this. And let me explain. Let's actually look at this and see if we can understand what this, how this works. Let's do the differentiable case. So in the differentiable case, what is a subdifferential? So your f is differentiable at that point. What's the subdifferential? What? It's a single point. Okay, it's a single point. So therefore, what's the supremum of of this single point? In fact, that single point is grad f of x, right? So what's the supremum of grad f of x transpose delta x? Sorry, there's no supremum because there's just one point. But then it just reduces to grad f of x transpose delta x. And then you get which is exactly what that's supposed to be. Okay, so it's linear. Okay, so that works out. And now let's try to figure out, like in this case, what it is geometrically. So here's the sub-differential. By the way, when you see a big sub-differential like that, actually, you should be visualizing what that function looks like at that point. Like, for example, is it sharp? First of all, is it differentiable at that point? No, because it's got a big old subgradient. Then, so it's clearly non-differentiable. And the question is it a knife? So, you know what I mean locally by knife? A knife is something that has two sides that go in like this that you can cut with. Or is it a needle? These are technical terms. I'm not insane. This is just, sure, I just made them up. They didn't exist 14 seconds ago. But they make perfect sense, okay? So is it a knife? Why not? Exactly. So a knife would correspond, a knife in the function, like this, a crease. Let's call it a crease. Whatever, it doesn't matter. If you had a crease, if the subdifferential gets big enough, it becomes a knife. It becomes dangerous. So, but let's just say it's a crease. So if it's a crease, but a one-dimensional crease like this, it means that actually in one direction it is differentiable, and therefore in that direction the subdifferential is small, and it would be a line, just like you said, a line segment. This is big, and so this means this is a point. This is like a needle. So in other words, at that point, oh, by the way, is that point global? Does it globally minimize? Is that point supported by a flat? Is it at the bottom? How do you know?
It's 0 isn't it?
0 isn't in it, precisely. So it's a point, but it's not at the bottom of the function. It's sort of off like that. So you have a point over here. Okay, so, and now you can actually calculate some things. So it says, if you go in this direction, by the way, does the function increase or decrease if I step in this direction delta x? Does it increase or decrease? I'm asking what's the sign of f prime of x semicolon delta x for the one shown? Does it increase or decrease if you go in that direction? It increases. Yeah, because, there's no scale here, but the point is, that point is positive. That dashed line kind of shows you it solves that little, in this case, that's an LP because I drew this as a polyhedron. That's an LP. That shows you the optimal value. It increases, okay? Now let me ask you a question. Suppose you say, okay, no problem. If I go in the direction delta x, the function will increase. You go, not a problem. I will go in the direction negative x. Please tell me what happens if you go in the direction negative x. Negative delta x, sorry. Negative delta x. What happens now? Unclear? No, I think it's clear. If you go in the direction...
Increase, and if you go in the other direction, it'll decrease.
That's true, it's not guaranteed. Okay, so let's, damn, I drew it the wrong way. Sorry. Do you mind? Let's just visualize this thing going down to here. It is, your answer was exactly correct. It's unclear because you'd have to project a normal out here. Well, what do you think? What do you think in this case? I think you decrease if you go in that direction. But let's imagine the subgradient went down here like that. It might have, right? So it goes down here. In this case, if you go in that direction, you go a positive amount, and that says you get this. So actually, here I can make another one. How about this? If I go in this direction, you increase. Why? Because the supremum of x2 over this thing, is the highest height you can go above this thing is positive. Go up. If I go this way, so if I increase x2 a little bit, my function goes up. If I decrease x2, my function goes what?
Up.
It goes up. Okay. So let's try that again. Okay. If I increase x2 a little bit, I increase the second coordinate, the function value goes up. You say no problem. Okay. So I will decrease x2 a little bit, and what happens to the function? It goes up again. Okay. So my comment on that is welcome to the world of non-differentiability, right? Because if it's differentiable, then if you go in one direction, if the function is differentiable, you go in one direction and the function goes up. then you just, no problem, you turn around and you walk the other direction and it's going to go down. Why? Because you get a linear approximation nearby. So, and if a linear function goes up in one direction, it has to go down in the opposite direction. Everybody, okay? So in this case, it means that that crease or point or whatever is such that if you move x1 and x2, it's going to, x1 and x2, if you move x2 up or down, the function goes up. Okay. Oh, let me ask you this. Let's see. Oh, we'll get to that in a second. Okay, so we'll get to the idea of a descent direction. So a descent direction is, well, it's what it sounds like. It's a direction where if you step a small amount in that direction, the function goes down. Yeah, some people, it can be less than or equal to 0 or less than 0, but let's not worry about that. So that's a descent direction. Now, for a differentiable function, the gradient is always a descent. Negative gradient is always a descent function. Always. You step small enough distance in the direction of the negative gradient, and the function will go down, assuming the gradient's not 0, right? So, okay. Now, for non-differentiable functions, this is the part that you have to sort of get. Subgradients are not like negative subgradients are not descent functions. Actually, this is going to be useful because later today we're going to have algorithms that are going to step in negative subgradient directions, and that's weird because you're stepping in a direction where the function goes up. You might ask, why would anyone do that? We'll get to that, but that's the story. So here's an example. It's this function, and this is a valid subgradient. That's a valid subgradient at that point. I mean, if you extend the line, you'll see it's a subgradient. Okay. Now, what would happen if you step in the direction negative g? You'd go in this direction, and you are pointing out. You're aiming out of the level curves. You're going uphill. So here, if you go in the direction negative g, you're going uphill. Okay. Then you say, no problem. Let's go in the direction g. How about g? Is it an ascent direction, descent direction? It's what? If you go in the direction g. It's an ascent direction. Yeah. It's worse. But the point is that you got big trouble here. So if you step in the negative subgradient direction, it is not a descent direction. Okay? So that's, I mean, that's, and you know, this is kind of, anyway, so that's it. It's kind of, but it's something that's very important to understand. So what's going to happen is for non-differentiable functions, the concept of derivative bifurcates into two things, and they're kind of duals, right? One is the directional derivative, and one's the subgradient. So half the stuff you know, half of your intuition about derivatives is going to extend, let's say 48% of the stuff is going to extend to the subgradient, and another 48% is going to extend to the directional derivative, and 4% will just be false in the non-differentiable case. I made those numbers up, of course. So, okay. Okay. So then you might ask, if you is there a way to characterize a subgradient? And there is, and it's very interesting, and it's going to be the key to understanding all of these. Well, I could write down the algorithms right now because they're one line. The algorithms we're going to write down. They're going to be one line, so we'll get to them later today. I could write them down, but to actually understand it, this is the key to it. Otherwise, it just looks totally bizarre, even though the proof is like 3 lines. Okay. So here it is. So what a negative subgradient is this. A negative subgradient is a descent direction for the distance to the optimal point. Actually, the distance to any point that's better than the current point. So actually, let's just go back and check that here. Yeah, here. Okay. So if you step in the negative subgradient direction, like this, I'm not going to write on it. Don't worry. Oh my God! Look at that. The whole time I could have. This is great. Okay. Wow. But now, it's not. I feel like I should. Oh well. Anyway. All right. So this is. Well, look at. I can actually see it now. So okay. So negative g is you step in this direction. We've already discussed. If you step a small amount in the negative subgradient direction here, your function goes up. Okay? Which does not sound like a winning move if you're trying to minimize the function. Okay? Or I should say, if you're trying to minimize it greedily, this is not what we call a winning move. Okay? However, the interesting part is that's the optimal point, the minimizer. And so what this thing says is if you step a small enough amount in this direction, your function went up, but your distance to that optimal point went down. And that is actually correct. Okay? So basically, we're going to see a bunch of algorithms. Boy, are they simple. And they're going to, but the Lyapunov function, so does everyone know what a Lyapunov function is? Or, so maybe no? Okay, so in tons of fields, you want to prove something converges, or something happens, or some condition holds. Like in, I don't know, in computer science, you want to verify that something always, some condition always holds. In for a dynamical system, you want to verify that a certain control system on an airplane will always, where you'll never deviate more than 100 feet from your altitude, or this kind of thing. In optimization, you want to prove that that an algorithm converges. And so people have lots of, very general approach to this is to come up with a function that decreases at each step. It may be the function you're interested in. For example, if you're minimizing a function, it could be the objective value. That'll be false here. But generally, it'll be in any case, it can be any old function, right? And it's a function that's just going down. And that's the key to kind of proving something converges. Okay? So that's called a Lyapunov function in control. It's called, in optimization, one name used for it, or algorithm design, is called a merit function. And you'd say the merit function goes down. Of course, I guess if it goes down, it should be called a dismerit. Anyway, it doesn't matter. It goes down. And it may not be what you want. It may not be the thing you're interested in. For example, it's very often in control systems, it turns out a lot of these functions, which are Lyapunov functions, they actually come from like energy-like calculations and things like that. Okay, so, all right. So what this means is, and by the way, all the algorithms you've seen so far for differentiable things, you've seen Newton method, gradient, scaled gradient, blah, 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 all these things, they're all descent methods. Oh, actually, we saw one that wasn't. We saw one that wasn't, exactly one, and that was the infeasible start Newton method. But all the ones that you actually messed with were descent methods, and in the sense that the merit function was the function. So at each step, the function went down. Of course, it's not enough to say that the function goes down at each step to prove convergence, except that it converges to some value. You still have to prove that the value it converges to is the optimal one. But that's the start. So it turns out here, what's going to go down in algorithms based on subgradients is not the function value. So the function value is going to go up. In fact, it's going to often go up. What's going to go down, actually, ultimately, is the distance to the optimal set. That's what's going down. Of course, you don't know what the optimal point is or anything like that, but at least this is what's going down. Okay. So to show this, you simply write this out, and you write out the square. I couple these two terms, and I get that norm squared. I get then the norm squared of that guy, that's here, and then I get this cross product. Okay? Now, here, I replace this with this, and this goes up because of my, my inequality here. That's just the definition of subgradient here. It says basically that, and G is the subgradient at X, or a subgradient at X, so that, I don't know, should I do this? Sure, why not? So it basically says, the following, that f of, let me get it right, here we go. You start from f of y is bigger than f of x plus g transpose. Should I have used x and z or something? Well, you use this one. And then you subtract. And I should have called that z maybe or something. I should have swapped these or something like that to get it the right way. Do I want f of z? Yeah. Let me make this f of z to make it work out nicely, like so. And then I claim that inequality shoved in here does the right thing. So it does, because you just switch it around. And that's f of, so this says basically something like this. F of x minus f of z is less than or equal to g transpose x minus z. Is that what I think that's what I want. And then that's good enough. So it says that, let's see, it says that this thing is smaller than that. It's a minus sign, so everything's cool. Okay? So All right, so, oh, and there's one more step of the proof. That's this. You choose, so actually, let's analyze the terms. I want that to be less than that, okay? That's not helping because it's positive. But it scales by t squared. Okay? This term absolutely helps because the assumption here is that f of z, this is less than that. If this is the optimal point, if that's x star, this is positive. In any case, by assumption, this is positive. And so that's a minus sign. T is positive. That's positive. So this is the good term, and that's the bad term. But the good term scales like t, and the bad term scales like t squared. So for small enough t, the good term overwhelms. And this thing is strictly less than that. Okay? So that's the picture. Just save that as an idea. Okay. Descent directions and optimality. So if you have a convex function, finite, near a point x, then two things either happen. Either zero's in the subdifferential, in which case you're done, right? By the way, this is not particularly useful unless, for that particular problem, you actually have a handle on a strong subgradient calculus or something. If you have a method to calculate the full subdifferential, then this tells you something. Otherwise, this is useless. Okay. Otherwise, if you're not optimal, there's a descent direction. And that says there's a descent direction. And in fact, the steepest descent direction is this. It's the smallest point in the subgradient, in the subdifferential set. Okay? And we can draw, let's see if I've even drawn some, but yeah. So here's a picture. So here's a subdifferential. Our function is quite pointed there, right? It's quite pointed. And 0 is not in that function, so that means there is a descent. It means, number one, you're not optimal. So then how do you find a descent direction? You find the smallest point in that subdifferential, and that happens to be that vertex shown there. Okay, I can use my new technology. Okay, there. So that's the closest point to 0. That's the smallest point in the subdifferential. And then if you go in the in that negative direction, that, by the way, this thing, that is a subgradient. Well, of course, because it's right here in the subdifferential. This subgradient happens to be an actual descent direction for the function. Why? Because if you find the smallest point, just the optimality conditions for finding the smallest point is that, well, if the smallest point were 0, you'd be done. So if it's not 0, it says if you go in the other direction, you're completely free and clear of this. And that says that there's actually a descent. And the distance here actually gives you the direction, something like the negative directional derivative. Okay, so that's the picture. So, by the way, let me ask you a couple of questions. Is this a descent direction, just going in that direction? See if how your eyeballs are doing.
Yes.
It is. Okay. How about if you go in this direction? Okay, there. How about that? Is that a descent direction? I think that one's kind of, what do you think? That was like, absolutely not. Because here, you would go out to a point there and you'd have very, the support function evaluated there is going to be quite large and positive. You're going to increase. That's like ridiculous if you go in that direction. Right? That's almost like the steepest ascent direction. Okay. And then down here is, how about, if I went along this axis, if I stepped along this axis, would it go down or up? If you go along this axis, what do you get? No, it goes up, way up. You evaluate the support function. You ask yourself, how far can you go in this direction in this set? And the answer is way over here, and that's way, way positive. So in this direction, you go down weakly, in fact. In fact, it depends on this little gap here. If you go in this direction, you go up pretty steeply. How about if you go like in this direction here? Is that a descent direction? If you go like, just say along this line here. Is that descent or not? No. That's an ascent direction. And if you go in this direction, ascent. Okay, so, but by the way, you couldn't possibly have this with a differentiable function, right? I mean, there's no way you could go have an ascent direction one way, turn around, go the opposite direction, and it goes up there too. So, impossible. Okay, so this is the picture. Actually, what this means is that there's this is the basis for a whole bunch of methods. By the way, not one of which we're going to look at for minimizing non-differentiable convex functions. It goes like this. It basically says the following. At each step, you get the subdifferential. Then you solve this problem. You minimize over the subdifferential the norm. If you find that 0 is in the subdifferential, which you would have to find if you actually solve this problem, then you stop and you actually have a proof of optimality because you have 0 in the subdifferential. Okay? Otherwise, you find the smallest point in the subdifferential and you step in the direction, the negative of that direction. And that's called steepest descent for non-differentiable functions. And we're not going to study it. It kind of works. And if you read more about these other methods, you'll find that that's sort of a theme. The methods that are sort of that are based on this kind of idea that work sometimes work quite well are things called bundle methods. But you will definitely see that if you poke around. It won't take you too long to find those. Okay, so this covers all our analysis of what is all that. See if I can. Oh, well, why not? Can I do that? No, let's see. Oh. That's interesting. Would I be able to do this? Let's see what. No. No. Let's see now. Okay. How about just finding a terminal? No, that's maybe dead because. Any hint? Sure. Okay. Everything's fine. Don't worry about a thing here. Sure. Okay. And that was. No. All right. Well, we'll just have to figure out what's here. Okay. That's better. Where is it? Subrad method. Slides. There we go. Is that going to work? Let's see. Look at that. See? Okay. Nope. Great. Yeah. There we go. Okay. All right. Okay. So what we did so far is just analysis. It's cool analysis. Some of it was not useful. I mean, basically, the stuff that requires strong subgradients, like the steepest descent stuff, that's not particularly useful. I think. I mean, or just it seems in practice it's not. Subgradient methods are. So these are. We're going to look at these. I can say a little bit about the history of these. You'll never guess where these come from. But actually, you might be wrong, because some people might argue they come from Kiev. So they're either from Kiev or Moscow. That's your only two possible choices. So you'd say both. Okay, so yeah, so guess what? These methods are from the Soviet Union in the 60s. You know, surprise, surprise. But what's so weird about these things is how simple they are. And they look really stupid. And in fact, I'll tell you a story about it in a bit. Okay, so here's a subgradient method. And I'm not kidding. It really is this simple. Here's what it is. Ready? You take the current point, you find a subgradient, and you step in the negative subgradient direction, multiplied by step size. I mean, so far, that's fine. And this is weak subgradient. Any subgradient, by the way, including a subgradient where the negative subgradient is not a descent direction. Now, by the way, what that means is this is not a descent method. You'll run this algorithm, and the function will go up at certain steps. Did you have a question? Yeah.
If I knew all the subgradients, which one would be the best?
Well, if you knew all the subgradients, you would probably do pretty well by taking the argmin of the norm, which would be the steepest descent one. However, interesting thing is, I think these methods are actually structurally slow. They're slow no matter what. So, in fact, the nice thing about these methods, the bad thing about these methods is they're slow. By the way, they're fast. They can be fast in theory. The bad news is that they're slow. The good news is, in a weird, perverse sense, the good news is they don't get much faster if you're much smarter and try to calculate fancy subgradients and things like that. They go from being like terribly slow to quite slow. Now let me explain why that's good news. That's good news because that's just work you don't have to do. So you don't have to write you can be totally sloppy, right? So, I'll give you an example. Suppose you're doing minimax and you have the maximum of 1,000 functions you want to minimize. That comes up all the time, okay? So, you could do this. You could evaluate, to evaluate the max, you have to evaluate all those functions, right? You have to evaluate 1,000 functions, calculate the maximum of those. Now, typically some will be tied. If there's no ties, no problem, right? But there'll be some ties. If you keep track of the ties and calculate that convex hull and solve a QP to get that best one, you could say, people look in the code, you'd say, look, I'm being super smart, I'm getting the best subgradient and all that, and this will work slightly better. So you went from, anyway, so it's not going to have a big effect. Okay. All right. So as I said, it's not a descent method. Because it's not a descent method, in a descent method, if someone stops you early and says, what's the best point you've got so far? It's the current point, right? Because you make progress every time in a descent method. So you don't even have the concept you only have the concept of the current point. So with a non-descent method, though, we'll encounter several throughout the class, actually. You need to keep a pointer to the best you've found so far. So if it gets worse, you keep going, but you save somewhere the best point you found so far. Okay, and we'll call FK best the best point found so far. Okay, so here are some step size rules. And let me remind you how this, when you first see this, you say, hey, that's the gradient method generalized to non-differentiable functions. Let me assure you it is not. It just looks like it. Okay, so, in fact, I can even tell you a story about it. So the first time I found out about these methods, I was a grad student. I was reading, and I got some Russian paper on something, and at that time, I guess still now, there's something called automation and remote, or one of these things that was translated basically by a company funded by the CIA, translated all the Russian papers badly. But I got very used to Russian typesetting because they just kept the typesetting the same. But the English was written by somebody at the RAND Corporation, something like that. So I conjectured that they didn't know what they were doing, and the original Russian, although I haven't verified this, had subgradient, but it got translated as gradient. So I'm reading this paper, I'm on like page 2, and it says, we'll just use a gradient method. So we'll just take a gradient, and I'm looking at it, I'm like, wait, just a minute. That function is non-differentiable. There is no gradient. But then it looked just like that. And I said, well, that's the gradient method for sure. This function is non-differentiable. There's no way. This can't be. And I thought, so then I had to go cool off and thought, okay, either this guy has no idea what he's doing. Like, this is the most fundamental thing, or there's something very interesting here. So it turned out to be the latter. So it was the subgradient method, badly translated as gradient. So you'll still find that. By the way, if you find Russian literature, you will actually find people referring to gradient meaning subgradient. So you have to be very careful. Okay. All right. So this is going to be it. Now in the gradient method that you know and love for differentiable functions, it works like this. You calculate. This is the gradient. And you calculate alpha k lots of ways. One way would be an exact line search. So you'd find out the best point. You could do a backtracking line search. Start with alpha equals 1, then times equals beta until you got some sufficient decrease. Everybody knows what I'm talking about, right? Okay. So you would choose alpha the step length you would never choose it ahead of time. You'd never say that my 14th step size is going to be 0.2. You'd wait until you got to the 14th iterate and try some step sizes. And if 0.2 was the right thing, that's what you would do, right? That's it. Okay. So here are the step sizes for the subgradient method. It's just the whole thing is looking really implausible, if you ask me. We start with the fact that you're going to move in a non-descent direction when you want to minimize a function. And the next part that really puts it over the top is that for these methods, you basically set the step sizes ahead of time. In other words, you don't even adapt them. I mean, there are fancier methods where you adapt what the step size depending on where you are. But basically, these methods work fine if you just say the step sizes are, for example, here, ready for some step sizes? 1 over k. So in the kth iteration, your step size will be 1 over k. Oh, by the way, if the function has some kind of domain issue, right? So you can't do 1 over k, you have to modify that. But the point is, here's one, just 1 over k. There you go. So the whole thing's ridiculous. I mean, here's some step sizes, all very implausible. You have a constant step size. Another one is a constant step length. That means that you get the subgradient here, you divide the step length, and that means that your actual, the distance you step is exactly gamma here, okay? Even more, these are just like, if you think it, these are just ridiculous, highly, highly implausible rules for step lengths. Another one that's going to come up is this, is step lengths which are square summable, but not summable. And so this would be, for example, 1 over k would be 1. And then you have non-summable diminishing, and this would be one where the limit of these things go to 0, but they're non-summable. Obviously, this implies that. So, so this is the weakest. And the classic example here is 1 over square root k, and why that is will come up in a minute. But so I just want to emphasize how silly this algorithm's looking. So it goes like this. It says you're at a point x, and you call get subgrad at x. So and this thing returns. It has many choices of subgradients. I mean, if it's non-differentiable, and it returns 1. And there's no restrictions on which one it returns. In fact, multiple calls at the same point could return different subgradients. It makes no difference. Doesn't even have to be deterministic. Just returns a subgradient. Okay. Which need not be, the negative of that need not be a descent direction. So it could be an ascent direction. So, and in fact, it could be even worse because your alpha is going to be positive. But in any case, it could be even a direction where either direction you step, the function goes up. Okay? Then you'd say, well, that's okay because there'll be a sophisticated line search to take care of that. No, the line search is basically, it's predetermined. It's just fixed. It's like 0.1. That's the line step. So, I mean, I don't know about you, but this is not sounding like super. I mean, it doesn't seem that promising when you first encounter this. Okay, so there's a couple of assumptions here. We'll just say let's assume that it's actually bounded below and there's an optimal x, and then we'll take a Lipschitz constant on the function f, and that's the same as saying that the subgradients are bounded by g. I mean, roughly. And then the other thing is, we'll take r to be the distance of our first iterate to the optimal point, so capital R. So actually, capital R, especially if it's an inequality, is something like it's a distance measure. It's measured in meters, if x were in meters. It's a distance measure of our ignorance, because it's how far. Before you start the problem, if someone has given you an x1 and an r and a g, and if someone says how far are you from the optimum, you have to say r. By the way, how far are you from optimum in terms of the function itself? You've done nothing. You've only been given the following data: x1, r, and g. How far off is f of x1 from f of x star? That has an answer. Rg, thank you. So Rg, R is your measure in meters, if x is in meters, of your ignorance. I mean, before you've even started. It's your prior ignorance. Rg is your ignorance in f star. Because if someone says, you have f of x1, and someone says, well, how suboptimal are you? You'd have to say, I could be up to Rg suboptimal, right? So actually, just bear that in mind, because Rg is going to come up. Okay. Oh, by the way, I should say that the proofs I'm going to give here are super simplified. You can go read the Russian ones if you like. They're actually a couple of pages longer, but they do away with, for example, this one. Okay, so you don't need this. This is just because I like proofs that fit on half a page or a quarter of a page or something like that. So, but I think this is the main idea. Okay, so here's some convergence results. It says if you run the subgradient method with a constant step size, then the following will occur. That the best, so the limit as k goes to infinity of fk best. By the way, this is the same as lim inf of fk, of fk, right? That's what it's of f of xk. It's the lim inf of that, because the best is the infimum and Did I say that right? I did, yeah. Okay, so this is, so anyway, this goes to f bar. I mean, this thing goes down because your best function value to date, that's monotonically decreasing. So it has a limit. We're going to call that f bar. This could be, of course, f star. But here's what you're guaranteed. You're guaranteed that f bar minus f star is less than g squared alpha over 2. And that says that if you use a constant step size, then you will end up being suboptimal, but with some number that you can actually say what it is. So you'll converge to suboptimality, some fixed suboptimality. Okay. Oh, I should say this. If the function is differentiable, then with constant step size, you actually converge if alpha is small enough. But for non-differentiable, that's absolutely false. You will not. And it's actually easy to see that. Actually, a good example is just to apply the subgradient method to minimize the absolute value of x. Okay? So let's just do that in our heads, right? So you take absolute value x. How do you get a subgradient? You're at a point x, and you get a subgradient for absolute value x. What's a subgradient? If x is positive, what's a subgradient? 1. It's plus 1. There's no choice. There's no other answer. If x is negative, what's the subgradient? Minus 1. If x is 0, you can return any number between minus 1 and 1. Okay? So for some reason, our code is going to return minus 0.75.
That's what, if you're gonna choose the minus 0.5 there.
Minus 0.5.
Yeah.
No, you mean 0.
Or 0, yeah.
Yeah. No, look. If you return 0, if you're at 0, you're making things easy because then the algorithm just terminates. Because if it returns 0 as a subgradient, that's the condition for optimality, and it can quit. Now, I don't want to do that. I'm going to return minus 0.75 just because some sick reason. Just who knows? Yeah?
But that goes behind to what I was saying, that if you choose specifically the
Yeah.
subgradient, then you can
I know what you're saying. Yeah. I'm telling you. It's not, it turns out everyone assumes this. So you can do a project on it. Everyone assumes, they think that this method, that by clever choice of the subgradient you can do better. That is probably a true statement, but it gets to be a huge, long, this is on a Pareto curve somewhere that trades off simplicity of code, which is to say one line, with simplicity of proof, which we will get to maybe, and is like 2 lines, and the actual how well it works, which is slowly. You can then have methods that are super complicated, try to estimate the best subgradient and blah, 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 and bundlement. They get all fancy and all that. Sure, they work a bit better, but they're like way longer and all that kind of stuff. So, but still, my basic comment on that is you'd be shocked how little you gain by being smart in returning a so-called good subgradient. So, okay. So anyway, let's imagine, make it simple, that you return plus 1 if you're positive, negative 1 if you're positive, and if you're 0, you return plus 1. It's a valid subgradient. Can't say it's not. Okay? So now you imagine where you are. You're somewhere, and we do a fixed step. Let's do a fixed, a constant step. They're the same, I guess, right? Because the gradient. Okay. So what happens is you're at a point x, and so you step alpha. If you're positive, you go down alpha. Everybody visualizing the subgradient method? So you go down. When you switch sign, now you go up alpha, right? So, and now you simply go back, you just oscillate like this. Everybody got this? Okay, so you are not optimal, right? Because you go there and it says the subgradient's plus 1, it says go that way, you step that way, your sign changes, you go the other way. So that's, so you can see that and that's, by the way, no matter how small alpha is, you will not converge because you'll end up in an oscillation like this. Okay. If you have constant step length, you again converge to something that's suboptimal. And here's the weird part: diminishing step size rule, it converges. So actually, what we won't do is, I think today we won't go over the proof of that, which is like shockingly short. But I just want to point something out. Ready? Here's some diminishing step sizes. How about 1 over k? Okay. So ready for the algorithm? Just put 1 over k there. Okay. And you now have, and now here's ready for the theorem? It's this. It converges to the global optimum. That's how stupid it is. I mean, you have to understand how dumb this is, right? It's basically, you know, for I equals 1 to whatever, from little k equals, whatever, little k equals 1 to some capital K, it's basically x minus equals subgrad f of evaluated at xk divided by k. That's it. That's one line. Okay? And it converges. I don't know if you're getting the thing. I mean, it's fine. You know, you might ask, well, why didn't we do this in 364? Well, this is kind of cool, but it's, I mean, these things, as you'll see, they're going to be very slow. They will have some redeeming features. But they're going to be quite slow. But still, this is very shocking if you think about it. You also could say that, I mean, if you also believe this meta statement I made last time, which went something like this, that if you can evaluate a function, you can evaluate a subgradient. If you believe that, then basically what this says is you can solve any convex function. Any convex problem for which basically you can, if you can evaluate the objective and constraint functions. We haven't gotten to the constraint case, but we will. But it says if you can evaluate the objective function, you can minimize it. Period. So everybody, and the algorithm is like it's barely a line. It's not a line. It's 15 characters, right? That's it. I mean, it's that stupid. It's weird. So when you first see this, it's kind of shocking. We'll continue this Tuesday. Actually, now that people are here, maybe I'll just repeat a couple of the things when people were in between this place. So the most obvious new development in the class is that we're here and and televised. But we'll try to keep it informal too, as well. So we'll just pretend it's not here. And if I say anything really totally off base, we'll just go into. I'll go to my friends at SCPD and we'll cut it out before it gets posted and the people at MIT look at it, and then I'm in big trouble, or the police get it, or whatever. So we'll do that. We posted homework 1, and I don't know that there are any other. Maybe there aren't any other announcements. So okay, so we'll quit here.